So I think it's time to start. So I'm very happy to, well, in the name of the organizers, welcome Pavel Kovtun, who has made many important contributions to relativistic hydrodynamics over the years. And tonight he will speak about hydrodynamic fluctuations beyond hydrodynamics.
Thank you. Thank you, Michal. So thank you also, Michal and George, for organizing this conference. I think it's very timely, very interesting. So thank you for inviting me to present those results. So what I will be talking about is what happens arbitrarily close to equilibrium in a macroscopic system. And I want to ask questions that are not specific to any microscopic model, whether classical or quantum, strong or weak coupling, quasi-particles exist or do not exist. Okay. So the simplest model of what happens in local equilibrium or close to equilibrium is classical hydrodynamics. And the way classical hydrodynamics works, so just to remind, in case there are maybe students who are not super familiar with this, it works like this. So you start with conservation laws for the energy momentum tensor and the current. Can you see my pointer when I move it here?
Yes, yes, we can.
Yeah, thanks. And when you look at the conservation laws, you look at this energy momentum tensor, and in d spatial dimensions, there is d+1 equations. And energy momentum tensor is symmetric, for it has d+1 times d+2 over 2 components. So you have d+1 equations for this many unknown functions. And so the current conservation is similarly one equation, has d+1 unknown currents. So there is not much you can do with this. And the way hydrodynamics simplifies this is it simplifies this by introducing some proxy functions. Okay, the proxy functions parameterize what the energy momentum tensor and the current are. So you have d+1 equations here. So you introduce d+1 proxy functions that you call beta mu vectors. And you have one equation here. You introduce one proxy function, you call it alpha. And the main assumption of hydrodynamics is to express the energy momentum tensor and the current as functions of those proxy functions. And then the number of equations is equal to the number of unknown functions. And then what you do next, you assume locality and maybe expansion and small gradients to write down what those expressions are, T and U as a function of beta and alpha. So beta and alpha is some proxy functions. As I said, they have no immediate physical interpretation. However, in equilibrium, you can give them physical interpretation in terms of velocity of the fluid, temperature, or the chemical potential. So this is how they are related to those proxy functions. Now, there are other formulations of hydrodynamics, Israel Stewart, for example, but all of them basically say that classical hydrodynamics is a couple of partial differential equations for some functions, such as beta of x and alpha of x, and maybe a few more functions. And what I want to do next, I want to look at very simple solutions of classical hydrodynamics. That is to see how the near equilibrium physical system reacts to infinitesimal external sources. So for a relativistic system, the external sources are the external metric and the external gauge field. And there is a well understood procedure of how to introduce the external metric G, external gauge field A, into those constitutive relations for the energy momentum tensor and the current. So what you do next, you solve these conservation equations. And when you solve them, remember these are equations for beta and alpha, you express your fields beta as a function of the sources, which is G and A, and alpha as a function of the sources, which is G and A. Then you take this expression, you plug them back into those hydrodynamic constitutive relations. And then you have a prediction of hydrodynamics, how the energy momentum tensor and the current, how they depend on the external sources. And in general, this procedure is hard to do. But if you are close to equilibrium, and if these sources are infinitesimal, you just expand to linear order in the sources, and this can be done quite straightforwardly. So you expand the energy momentum tensor, There's a term that is linear in the external metric, term that is linear in the external current, and there are some coefficients. The coefficients I call G sub RET, and they have some indices so that the whole thing works in terms of index contraction, and the same for the current. There's some coefficients in front of delta G and delta A. Okay. Now, the linear response theory tells you that those coefficients that sit in the classical solutions of your hydrodynamic equations that multiply those infinitesimal sources, that those coefficients actually have the interpretation of retarded functions. So classical hydrodynamics gives predictions for retarded functions of conserved densities and fluxes, the special current stress, in equilibrium. Okay, or close to equilibrium. For example, if you look at the retarded function of, say, charge density, it has this form. So capital D is the diffusion constant, chi is the susceptibility. There is a singularity here that reflects essentially the fact that it comes from the diffusion equation and reflects the existence of hydrodynamic modes. And if you look at correlation functions of the fluxes, so in this particular example, I have G, X, Y, X, Y. So this is X, Y, two-point function of the stress. Say it's zero momentum, there are no singularities. It has this form, P is the pressure, eta is the shear viscosity. Okay, and so these predictions for response functions, they do not depend on which version of hydrodynamics you choose to use. So these are universal predictions of classical hydrodynamics for observables. And formulas like this, they give rise to so-called Kubo formulas, how you express, say, the viscosity or the conductivity or the diffusion constant in terms of response functions. Okay. So the question that I want to ask is this: are these predictions of classical hydrodynamics actually correct? Okay, after all, classical hydrodynamics, meaning hydrodynamics viewed as a collection of partial differential equations, is just a toy model of fluids. And nature may or may not care for our toy models. So if you think about limitations of hydrodynamics, there's one particular limitation of hydrodynamics that will be important for what I'm talking about. So of course, macroscopic stuff is made out of microscopic stuff. And if you think about analogy with, say, quantum mechanics or quantum field theory, in a quantum vacuum, virtual particles are constantly produced and absorbed due to quantum fluctuations. Similarly, in a macroscopic state, virtual sound waves are constantly produced and absorbed due to statistical fluctuations. And the sound waves will backreact on the macroscopic physics. This is because hydrodynamics is nonlinear and waves interact. So what I have here is a cartoon how, say, temperature, fluid velocity, depend on distance. So this thick line is a solution to the classical hydrodynamic equation. And this little dots is supposedly the microscopic stuff that the fluid is made of. And a result of the fluctuations here, there will be sound waves emitted by those fluctuations. And the sound waves emitted are denoted by these thin lines. And these thin lines is going to interact with this big, thick line. So this back reaction will be important. So the claim is this: even if you're interested in macroscopic long distance response near static equilibrium, then classical hydrodynamic equations which ignore the back reaction, they can lead to predictions which are qualitatively wrong. So I emphasize this is for macroscopic response, not microscopic, and the predictions are qualitatively wrong, not quantitatively. And this has been known for a long time. I have a reference here from Alder and Wainwright. So this is the early days of molecular dynamics. They basically took a gas of billiard balls, billiard spheres, and asked, do they obey Navier-Stokes equations? And they found some surprises. So the rest of my talk will be comments on this claim. So an example that I want to think of is viscosity. So what is viscosity? Viscosity is something that tells you about the transfer of momentum between layers of fluid. So here I have a picture of fluid that moves from left to right. Yellow lines denote the flow of my fluid, and blue lines denote the particles that jump between the layers of fluid. Here, viscosity is related to the relationship between stress and the divergence, not the divergence, derivatives of the fluid velocity. And it can also be related to correlations of stress. So the retarded function, as I said earlier, has this viscosity multiplying the frequency. And in a gas, the viscosity is proportional to the mean free path of these blue molecules. Okay, so this is something that is well known. Now, if you think about this fluctuation picture, then you realize that momentum can also be transferred by collective excitations. And in a gas of sound waves, how far sound waves propagate, it also depends on the viscosity. So the mean free path for sound waves will be inversely proportional to the viscosity. And of course, there is k squared because long wavelengths, sound waves propagate for longer. And if you think about the contribution of this gas of sound waves to viscosity, basically you have to sum over all possible momenta here. So d is the number of spatial dimensions. And you sum your mean free path. And the mean free path depends on k. And what happens here, if you do this integral, if you're in 3 spatial dimensions, well, the integral is UV divergence. So this is some UV cutoff lambda. And it will be inversely proportional to eta over s, viscosity over entropy. And in 2 spatial dimensions, it will be infrared divergent. Okay, so the simple estimate tells you something. So this is the physics of thermal fluctuations. It is invisible if hydrodynamics is viewed just as a collection of partial differential equations. So if you think that viscosity over entropy can be arbitrarily small, well, think again, because the correction to viscosity is inversely proportional to the viscosity. And the last comment is that because there are divergences in 2 + 1 dimensions, this tells you that classical hydrodynamics may well be just plain wrong in 2 + 1 dimensions. So how does one describe these effects quantitatively? The next best toy model after hydrodynamics that does not care about the nature of the microscopic constituents is so-called stochastic hydrodynamics. And the way it works is you take the stress energy tensor, and it's equal to what you get from classical constitutive relations here, and you add some random stresses. And same for the current, you add some random fluctuating currents. When you think about the averages, statistical averages, this is average over the noise. So what does it mean to average over the noise? This means you take the path integral over the noise with some weight. So exponential minus the action of the noise. So what is this action of the noise? So this action for the noise, you can argue it's Gaussian, meaning it's a quadratic function of the noise for long wavelengths, fluctuations by the central limit theorem. Because there are many microscopic volumes that fluctuate inside one wavelength. Now, the width of the Gaussian in this noise action is determined by demanding that the equilibrium 2-point correlation functions satisfy the fluctuation dissipation theorem. So there's a relationship between symmetric function and the imaginary part of the retarded function. And the way you can use the stochastic hydrodynamics is roughly speaking like indicated in this picture. So you take the energy momentum tensor, and it has some contributions that are linear in the velocity, temperature, whatnot. And it has this very simple non-linear term, energy density pressure and VI, Vj. Okay, this just comes from boosting the equilibrium stress tensor. And it has some noise here. And so when you think about correlations of stress, then you will get this naive contribution that comes from classical hydrodynamics. And then you will get correlations that come from this term. So you can represent pictorially this as a diagram. We have E plus P sitting at each vertex. And because there are 2 velocities coming at each vertex, you have 2 legs coming out of each vertex. You connect them. You write down the propagators. You integrate over the loop. So that's how you get something that resembles this picture on the right. So you can do this more systematically with stochastic hydrodynamics. And so this is what you find for stress correlations, let's say in 3 + 1 dimensions. Okay, so this is retarded functions of stress, a function of stress. And the terms that are indicated in red, these are the terms that come from classical hydrodynamics. So P from classical hydro minus I omega eta, first order hydrodynamics, something that has omega squared, second order hydrodynamics. Now the terms that are in purple are the terms that come from this one loop statistical effects. There will be some fluctuating correction to pressure. There will be a cutoff dependent correction to the viscosity that is inversely proportional to the viscosity. And there will be a term that is actually independent of the cutoff. It has a fractional power of frequency, and it's again inversely proportional to eta over s. So this is the one loop fluctuation correction to the retarded function. So if you think about the physical viscosity, it actually includes all of these corrections if you somehow can cleverly compute them. So what you can see is that small viscosity implies that the corrections to the naive viscosity are large. So this tells you that fluctuations are mandatory for small viscosity physics. What this also tells you that fluctuations are more important than second order hydro, because omega to the 3/2 is more important than omega squared. And these contributions, they're cutoff independent, they're universal, they're determined by thermodynamics and the viscosity. So what else you can see? So in real time, this omega to the 3/2 gives an inverse power law decay, 1 over t to the 3/2. This is what people call long time tails. So this is an algebraic decay of correlations. It's actually more important than first order hydro if you think about real time, not about frequency. In 2 plus 1 dimensions, we have this omega to the power 3/2 becomes omega log omega. And what this tells you is that this eta now here gets a correction that is proportional to the logarithm of omega. And the Kubo formula instructs you to take the limit omega goes to 0, and that blows up. So this tells you that Kubo formula for viscosity does not exist in 2 plus 1 dimensions. And the last comment from here is that if you think about, where different factors of n go, if you work with a large n theory, then you realize that the large n limit does not commute with the hydrodynamic limit, and hence those fluctuation effects are not visible if you, for example, do classical holography. There's a neat analogy with quantum gravity, perturbative quantum gravity. So what happens in hydrodynamics is that if you look at the correlations of stress, you get contribution from perfect fluids at order 1, contributions from Navier-Stokes at order omega, contributions from 2 derivative hydro at order omega squared. But then you have something that is 3/2. It's more important than high derivative hydro. And with quantum gravity, what happens? You can look at the potential between two particles. And the potential between two particles, it will have from classical gravity, it will have something that comes from the Einstein theory. And then if you add high derivative corrections, these high derivative corrections will come suppressed by some scale, Planck scale, whatnot. And so the contribution to the interparticle potential that they give is going to be like Yukawa type contribution. So they will decay exponentially. However, what you can do, you can compute the contribution to the quantum contribution from a perturbatively quantized Einstein gravity in flat space. The graviton exchange, the graviton loop that contributes to the interparticle potential, as was done here by Biron, Bohr, Donahue, and Holstein, and you will realize that's an algebraic decay. That's actually its quantum correction that's more important than the classical high derivative correction. So that's something that's completely analogous to what happens in hydro here. So the bottom line is this. If you use the classical hydrodynamics, meaning hydro is PDEs, if you use that to evaluate the response to infinitesimal, low frequency, low momentum sources, that's unreliable. You cannot trust this. Short time statistical fluctuations, they give rise to infrared late time correlations. The deviations from classical hydrodynamics are more pronounced at small viscosity. And stochastic hydro predicts that these infrared correlations are universal. They're determined only by thermodynamics and transport coefficients such as viscosity, conductivity, etc. So this is something that is well known, has been well known in statistical physics in the 1970s. In relativistic hydro, this has been emphasized, in more recent years. But this is well known. So I want to talk about things that are newer than that. So the problems of classical hydro don't end here. So this is true, especially if you want to do high derivative hydro. So what happens if you want to go beyond the naive stochastic hydro? So you can ask several questions. So let's talk about the noise first. So the action for the noise is only Gaussian in the limit of strict momentum, strict limit momentum going to 0. So what if you want the derivative expansion that takes you beyond the strict leading order k goes to 0? Okay, maybe the noise is not Gaussian anymore. How do you take that into account? So the width of the Gaussian, that was fixed by the fluctuation dissipation theorem for 2-point functions. But fluctuation dissipation theorems, they exist for all n-point functions. This has been discussed in great detail in this paper by Heinz and Wan. So how do you incorporate those fluctuation dissipation theorems for n-point functions? So another thing that you can ask is this. Classical hydro can only compute retarded functions. So if you have some response function that's not retarded, those are invisible to classical hydro. So if you're looking at 2-point functions, the non-retarded 2-point functions can be related to retarded 2-point functions by the fluctuation dissipation theorem, same for 3-point functions. But if you go to higher order, higher point functions, this is not true. Higher point non-retarded functions, they cannot be related to retarded functions through these fluctuation dissipation theorems. Hence, those non-retarded functions, they contain new low energy information. So how do you access that information? How does that information feed back into the physics of hydrodynamic fluctuations and correlations? So the approach that people started thinking about recently is the approach of effective field theory. So we are more or less used to using effective field theory to compute correlation functions. So you identify the low energy degrees of freedom psi, you identify some symmetries G, you write a local action that depends on psi and the external sources. That action has to be invariant under the symmetries G that you have. Then you get your correlation functions from the generating functional that you obtain by integrating over your fields weighted by some action that depends on the fields and the sources. Okay, so that's what you do in effective theory. So can you do the same for hydro, for near equilibrium states? So in such an effective field theory, classical hydro will be the Euler-Lagrange equations of motion that come from the action. Stochastic hydro will emerge as a leading order truncation. So what are the building blocks of the EFT? So you want the normal symmetries: locality, gauge invariance, different invariance, maybe time reversal, parity, the normal symmetries. Then you want the Euler-Lagrange equations of motion. You want those equations of motion to be the conservation laws, conservation of the energy momentum tensor in the current, right? So this is slightly different from what we teach our students in classical mechanics. So what we teach in classical mechanics, we teach our students that Euler-Lagrange equations, they imply conservation laws, that they're stronger. So, but here we want the Euler-Lagrange equations to actually be the conservation laws, because these are the equations of motion for hydro. So also we want access real-time correlation functions. So hence you want to formulate effective field theory using the Schwinger-Keldysh fields, meaning you need 2 copies. You need to formulate a theory on a time contour that runs back and forth in time. And for equilibrium states or near equilibrium states, you want to impose Kubo-Martin-Schwinger constraints. And it would be very nice if you could impose this constraint as a symmetry. Okay, so
I'm sorry,
yeah?
I really don't want you to stop talking, but the organizers
I'm out of time.
Have obligated me to stop you within a couple of minutes, let's say. I just saying.
Okay, couple of minutes. Okay, right.
Like,
okay, good.
Well, let's say 4.
Okay, yeah, yes, I can finish in 5 minutes. Yes. All right. Okay, so I probably will skip that. So this is some building blocks for diffusion, effective field theory for diffusion. So I will also skip that. So this is the diffusion, discussion of diffusion in stochastic hydrodynamics. So maybe what I will say is this. So if you formulate stochastic hydrodynamics in the simplest possible hydrodynamic theory, which is diffusion, there is a well-defined procedure to convert stochastic differential equations into a path integral with some action. Okay, so this will be the action that you will find for diffusive fluctuations. So the thing they need to know about this action is that it has a certain type of field, which I denote with the superscript A. So this is the field such that if you take the variation with respect to that field, you will find, and set that field to 0 at the end, you will find the classical hydrodynamic equation. This is the stochastic field. Okay, so and the action for diffusion, it has something, it has a term that is linear in that field times the diffusion equation. So this is the diffusion equation. You may not recognize it, but this is the diffusion equation. And it has something that is quadratic in that stochastic field. And that thing that is quadratic in the stochastic field, it comes with derivatives of that stochastic field and has two indices. So it can have a term that is proportional to the Kronecker delta times some coefficient, mu is the chemical potential, it's what you think it is. And it has some term that is proportional to the derivatives of mu. Now, if you think about what happens in classical hydrodynamics, in classical two-point fluctuation dissipation theorem, then that fluctuation dissipation theorem will tell you what this thing is. But it will not tell you what this thing is. So this coefficient theta here is something that you will not be able to figure out if you do stochastic hydrodynamics with the naive fluctuation dissipation theorem for two-point functions. Okay, and actually this coefficient is something that is sensitive to non-retarded functions. So you can also do effective field theory for diffusion that you can read about in this paper. So this is something that I probably skip. So this is how the KMS symmetry works for those systems. So what I want to say is this. So if you carefully do the effective field theory for diffusion, if you really not do just stochastic hydro, but if you really do this effective field theoretic approach, then what you will see is that your effective field theory has new vertices that you would not be able just to guess if you naively do your stochastic hydrodynamics with the Gaussian noise and the fluctuation dissipation theorem for two-point functions. It will have new interactions. So the wavy lines here are the stochastic fields, and the solid lines are the normal classical fields. And what this effective vertices do, they give rise to infrared effects. So I don't have time to talk about those infrared effects, but I will tell you about the summary. So the summary is this. So the only thing you need to know is this. There are two types of fields. So I'm finishing in 1 minute. There are two types of fields. One is the classical field that you call phi r, and one is the stochastic field, which you call phi a. The action, the effective action, can be organized as an expansion in powers of those A-type fields. So the A field is a stochastic field. There are terms that are linear in this stochastic field times some complicated functions of the classical fields. So these functions contain all the classical hydro, all the nonlinearities, all the interactions of classical hydro that I contain here. Terms like this, some of these terms are fixed by the fluctuation dissipation theorems in terms of the classical transport coefficients, such as the viscosity, heat conductivity, whatnot. There are also terms that are quadratic in the noise fields that are not fixed by the fluctuation dissipation theorems, and they're actually invisible to classical hydrodynamics. And the terms that have more than 2 powers of the fluctuating field are completely invisible to classical hydrodynamics. Now, these are new interactions. You can call them stochastic transport coefficients. So these stochastic transport coefficients, they're invisible to classical constitutive relations, like purely invisible, but they contribute to measurable correlation functions through loops. These stochastic transport coefficients, they give rise to infrared effects, though they would be derivative suppressed in 3+1 dimensions. Now, these are different effects from the usual long time tails. Why are they different? They're different because the usual long time tails are determined by the viscosity and thermodynamics. These effects are determined by something that is completely invisible to classical thermodynamics. If you want Kubo formulas for these stochastic transport coefficients, the Kubo formulas for them involve non-retarded functions, unlike the Kubo formulas for viscosity, conductivity, whatnot. Thus, if you know the macroscopic classical effective theory to all orders in the derivative expansion, that is not enough for you to correctly describe macroscopic, I emphasize, macroscopic infrared correlations. And the question that I want to know is, of course, in which systems are these new stochastic effects observable. So I'll stop here. Thanks for listening. Sorry to go over time. Thanks.
Thank you very, very much for this thought-provoking talk. I think I'm going to manage being the first person to ask a question because I don't see any hands raised. Oh, no, Gabriel de Nicole has a question. Please ask it.
So thank you for the very nice talk. I couldn't raise my hand because I couldn't find the button. I mean, in the previous session, I could see the raise my hand thing, but it vanished for me. So that's why.
Maybe because you're a co-host. Co-hosts cannot raise hands.
Really? Ooh. Okay. So my question actually has to do with your, when you apply this power counting scheme for the gradient expansion, right? You compare terms of order omega squared, and also this omega 3/2 that appears due to fluctuations, right? So, for example, if there are no fluctuations, there are several examples of these series that diverge, right? You do the gradient expansion, and then this series doesn't converge.
Yep.
The zero rates of expansion. And so in this sense, possibly maybe the series also is ill-defined when you add fluctuations. So then how can you really compare the terms order by order? I mean, what does it really mean to say that, a given term, is dominant compared to the next term if the series itself doesn't exist?
Yes, good question. And I think it may depend on the type of physical question that one is asking. So if you are specifically asking about, say, 2-point near equilibrium functions, so it's not just omega to 3/2. You go to higher loops, there will be all kinds of fractional powers of frequency. And what this tells you is that, yes, it does not even make sense to even ask questions about the convergence of the derivative expansion, because these questions are only formulated in classical theory. And here there are these branch cuts that are more important than those things. So in the language of holography, people sometimes, myself included, talk about limitations to convergence of derivative expansion that come from collision of singularities in the complex frequency plane. But what this tells you is that there is a whole bunch of branch cuts happening in that frequency plane, in that complex frequency plane. And it's those branch cuts that are going to actually dominate the late time physics. Now, however, if you're asking a question that is not the question about correlations, if you're really asking a question about the initial value problem for 1-point function of the energy momentum tensor, I actually have not thought carefully about how these effects would be manifest there. So this is something that's maybe more related to Goche's talk on Friday, when he talked about these relations for actual kinetic theory analog for fluctuations. But I have not thought about what happens if you just actually look at the time evolution of 1-point function from given initial conditions. But if you look at like 2-point functions, 3-point functions, it's clear that these effects are going to be more important than this high derivative terms in classical constitutive relations.
Thank you.
Okay, we have another question from Romuald Janik.
Hi, Pavel. Thanks for a very, very nice talk. I wanted to ask about what's in holography. Those stochastic terms would arise from like one loop effects on the gravity side for gravitons, or something more complicated?
Yes. Yes. They would. So they would arise from loop effects. I mean, if you do naive counting for these terms, there will be 1 over n squared suppressed. And there was a paper in 2009, I think, by Saremi and Karonot that actually massaged those hydrofluctuation calculations into the ADS-CFT calculations with the graviton loop in the bulk. But it's not like they actually started with let's quantize supergravity in this background. It's more like it was more like the answer analysis and trying to argue that actually yes, one loop graviton effects in the bulk, they can give rise to precisely those effects.
Okay, thanks a lot.
Okay, there's another question from Søren Schlichting.
Yeah, hi Pavel. I had a question. I have two questions actually. So one is on your last slide. I wanted to understand what's the difference between these quadratic in the noise term fields that contribute and that do not contribute to classical correlation functions. And the second question would be I mean, you wrote down these horribly complicated terms that you get somehow in your action or in your effective action. I was wondering whether there's any understanding of how these behave, how these, so to say, the associated couplings behave under renormalization group flow. So if you integrate out fluctuations, whether you need essentially all the terms in this, all these complicated terms in your infrared effective theory, or whether some of them are actually go away.
Right. So right. So in terms of classical constitutive relations, classical hydrodynamic equations, so all of these things are contained in this capital F. So why is this? So this is because classical equations of motion arise by taking the variation with respect to the A field, and then you have to set the A field to 0. A field is like the quantum fluctuation field or statistical fluctuation field.
Yeah, sorry, I meant the second line terms, actually, the quadratic ones. Which ones? Why are some fixed and some are not?
Right. Yes. Then, so once you have those things, you say you ask the question. So those terms by themselves, they will not be necessarily invariant under the KMS symmetry. Okay, so they will not necessarily respect the fluctuation dissipation theorem. Now, then what you say is you say the following: oh, let me demand that the fluctuation dissipation theorem is respected. Then I have to add something to the action to make sure that the fluctuation dissipation theorem is respected. And you add that second line. So that second line is what you add to the action to make sure that the first term is consistent with the fluctuation dissipation theorem. But then you realize that you can add other terms that are consistent with the fluctuation dissipation theorem within themselves, without having to mix with the classical equations. And so that is the difference. So these ones, fluctuation dissipation theorem relates the second line to the first line, to the classical equations. But these things, they're already KMS invariant without any connection to the classical equations of motion. So that is the difference. Okay. And to very briefly comment is that those terms will be less there. They will be derivative suppressed, so they will be less relevant that the interactions, let's say, that come from this classical ones.
Okay. Well, we started the talk a little later, so I will prolong the discussion just a little bit. Hong Yi is the next person.
Yeah. Hi. This may be a simple question for you, but. So this two type terms, so you are looking at, is it correct that the first term represent kind of a multiplicative noise, and the second term represents some non-Gaussianity in the noise?
Yes, you can say it like this. Yes.
And just a quick follow-up question. So
I mean, non-Gaussianity is here. So these quadratic ones, they're still Gaussian. But yes, I just wanted to emphasize that not everything that is Gaussian is fixed is related by the fluctuation dissipation theorem to the classical equations of motion.
Yes, yeah. I think it is very natural to expect this kind of corrections. But my question, if I allow to ask, is that for the non-Gaussianity of noise, since the noise usually represent the effect of the background to the mode you are interested in principle, shouldn't you expect that the non-Gaussianity of the noise should be governed by a different small parameter than the other sources of non-Gaussianity for the mode itself, like effective?
Yes, and it is governed by different parameters. So it is governed by this, but what I call stochastic transport coefficients. So this Gaussian noise is, the strength of that noise is governed by things like viscosity or diffusion constant conductivity, right, according to the standard fluctuation dissipation theorem. But the strength of the non-Gaussian noise is governed by these genuinely new parameters, which, here I call the stochastic transport coefficients. Is this roughly what you were asking? Sorry, or maybe I misunderstood.
Yeah, I was asking a slightly different thing, but I think we can talk later. Yes, because I don't want to hijack, the schedule.
Okay, there are two more hands raised. Then so it's Gotcha Bassar. Please ask your question.
Hey, yeah, thanks for the very nice talk. So I think Søren sort of asked a similar question, but it seems like these terms that you introduced, they seem to be very natural terms in terms of, if you think in terms of VFDs, like some higher dimension operators.
So yeah, that's what they are.
Are they sort of, how do they behave under RG? Are they sort of, can I think of them as some irrelevant terms? That sort of
they are irrelevant in the same sense as, you know, viscosity is irrelevant compared to perfect fluids. The contributions of these terms to correlation functions will be derivative suppressed, right? So if you ask about, you know, the actual manifestation of those terms in, you know, quark-gluon plasma, you know, I don't necessarily believe they will be, you know, of much importance. But, you know, we haven't worked out these things for relativistic fluids, so I shouldn't be saying this. So for me, this was more of a matter of principle. And as a matter of principle is this: if you want to access, you know, algebraic correlations, not exponential decaying correlation, but algebraic correlations, then these terms that are completely invisible to classical hydro, they give you long-range correlations in time. So this is real-time physics, of course, it's not Euclidean physics. And they do contribute to infrared effects, but they are subleading, so they're derivative suppressed. So in the simple example of diffusion, of the diffusion model, they will be less important than two derivative hydro, but they will be more important than three derivative hydro. These terms that are invisible to hydro, to classical hydro. And you know, there's a lot of suppression there because diffusion interactions, they come derivative suppressed already. So if you work in actual hydrodynamics that does have conserved momentum, so this will make these effects more important because those interactions like this, they do not have derivatives, so they're not suppressed. No.
Thanks. Yeah.
Okay, we don't really have, but let's have one last question from Mauricio Martinez, the last one today. I mean, to this talk.
Thanks. So Pavel, nice for the nice talk. So I just have a question regarding the possible effects that you can be measuring, because in general, fluctuating hydrodynamics, although it's important as you emphasize in your talk, it's extremely hard to get measurements there, even in 2+1 condensed matter systems like in collatoms. And Thomas made the point in the chat that it has not been seen in practice. So what is your comments on this regard, like where people should look experimentally and theorists to make precise predictions and with possible experimental consequence, and not only in quark-gluon plasma, but let's say condensed matter systems? What is your opinion on that?
Yeah, so my thought is that really the best bet would be in one-dimensional systems, 1+1 dimensional systems, edge states of some two-dimensional materials. So those would be the systems where all fluctuation effects are generally more pronounced, and so this I think is maybe the best hope for these effects. But if you ask me, have I worked this out in a particular, you know, model of you know, one-dimensional condensed matter system? No, I have not.
Thank you very much again for this great talk, and I think it's time for the next